+16786484277. You can mail us at support@economicsexinghelp.com or reach us at www.economicsexinghelp.com/. Problems 1. Consider the n times repeated game with the following stage game. A. Find a lower bound pi for the average payoff of each player in all pure strategy Nash equilibria. Prove indeed that the payoff of a player is at least pi n in every pure strategy Nash equilibrium. Your grade will be 10 pi dot. B. Construct a pure strategy subgame perfect Nash equilibrium in which the payoff of each player is at most n+1. Verify that the strategy profile is indeed a subgame perfect Nash equilibrium. 2. Consider the infinitely repeated game with discount factor 0, 1 and the stage game. For each of the strategy profile below, find the range of under which the strategy profile is a subgame perfect Nash equilibrium. A. The play is ILR if ILR has been played at all previous days and XLL is played otherwise. B. On Sundays, i.e. at T 0, 7, 14 XLL is played on other days. ILR is played if ILR has been played at all previous such days and XLL is played otherwise. C. On Sundays, XLL is played on other days. IRR is played if IRR has been played at all previous such days and XLL is played otherwise. 3. Consider the infinitely repeated prisoner's dilemma game with discount factor and is equal to 0, 999. The stage game is A. Find a subgame perfect Nash equilibrium in pure strategies under which the average payoff of each player is in between 1.1 and 1.2. Verify that your strategy profile is indeed a subgame perfect Nash equilibrium. B. Find the subgame perfect Nash equilibrium in pure strategies under which the average payoff of player 1 is at least 57. Verify that your strategy profile is indeed a subgame perfect Nash equilibrium. C. Can you find a subgame perfect Nash equilibrium under which the average payoff of player 1 is more than 5.8? Recall problem 4 in homework 2. Consider the repeated game with the following stage game. A unit mass of kids are uniformly located on a street, denoted by the 0-1 interval. There are 2 ice cream parlors, namely 1 and 2, located at 0 and 1, respectively. Each ice cream parlor sets a price less than or equal to for its own ice cream, simultaneously, where 0.1 arcade located in is to pay cost vertical bar to go to a store located at where 0p3. Given the prices 1 and 2, each kid buys 1 unit of ice cream from the store with the lowest total cost, which is the sum of the price and the cost to go to the store. If the total cost is the same, she flips a coin to choose the store to buy. A. Assume that the above game is repeated 100 times and find the subgame perfect Nash equilibria. B. Assume that the above game is repeated infinitely many times and the discount rate is 131. For each of the following strategy profile, find the highest under which the strategy profile is a subgame perfect Nash equilibrium. Here may be a function of. You need to choose both and to make the strategy profile a subgame perfect Nash equilibrium. 1. At the beginning, each parlor I chooses pi is equal to p asterisk and continues to do so until some player sets a different price. Each selects price pi is equal to p thereafter. 2. There are 2 states, collusion and war. The game starts at the state collusion. In collusion state, each player I chooses pi is equal to p, and in war state each player chooses pi is equal to p. If both players set the price prescribed for the state, then the state in the next round is collusion. The state in the next round is war otherwise. 1. Bonus, in part. 2. Assume that p greater than or equal to 0 but war can last multiple periods. State such a strategy profile formally and answer the above question for such a strategy profile. Problem 1. The lower bound is 1. If n is even, let x be C, C be B where C, C is played for n/2 periods and B, B is played for n/2 periods. For n odd, x is equal to C, C B, B A where C, C is played for n1 2 periods, B, B is played for n1 2 periods. The Nash equilibrium strategy is to play x as long as x has been played in every previous period and otherwise play C, C for the rest of the game. This is a Nash equilibrium because there is no possible deviation for either player. If a player deviates, he will get payoff at most 1 in every future period, so the best he can get by deviating is payoff n, which he is indifferent to. B for an even, xn is equal to C, C B, B A where C, C is played for n/2 periods, B, B is played for n to 1 periods. If n is odd, let x be C, C B, B where C, C is played for n1 2 periods and B, B is played for n+1 2 periods. For n is equal to 1, the strategy is to play B, B for payoff 2. We prove by induction. Suppose that for nt, there is a subgame perfect equilibrium with payoff n+1. At n is equal to t, the subgame perfect equilibrium is to play xt as long as everyone has played on the equilibrium path. If a player deviates from playing C, C at some period with t rounds remaining, we play xt as punishment. If a player deviates from playing B, B or A, we continue on xt. Solutions. A player that deviates with t rounds remaining gets payoff 1 in that round, and then plays the xt subgame perfect equilibrium with payoff t+1 for a total of t+2. This will never exceed t+1, so on history's equilibrium pathere are no profitable deviations. There are no deviations after histories when we are on xt because they are subgame perfect equilibria by the inductive hypothesis. Problem 2. A. This is never SPE. Player 2 has payoff 0 in equilibrium, so he can always deviate to R for payoff 1. B. This is also never SPE, for the same reason. C. This is always a SPE. In every period, players are playing a stage game Nash equilibrium, so the strategy is subgame perfect equilibrium. Problem 3. A. Suppose for each cycle, C, C is played a times and D, D is played B5 A plus times. Then average payoff for the cycle is 5 A plus B. To make 1.1 we A plus B need 19 AB 39A. Let's choose A is equal to 1, B is equal to 20. The strategy profile is for each player. Play D for T is equal to 21K plus I, for I is equal to 1, 2, 20 and play C for T is equal to 21K if no deviation has occurred. If any deviation has occurred, play D forever. No player has incentive to deviate when some player has deviated since D, D is name of the stage game. When a player is supposed to play D at T is equal to 21K plus I, to prevent deviation we need Note that the right side of inequality is minimized